let us move to the third technical session by Professor Shobhana Narasimhan. She is a professor at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. And she received several awards like Sri Shakti Saman Science Award, Kalpana Chawla Women Scientist Award, and International Union of Materials Research Society Young Research Award, Material Research Society Award, and several institute, university, and college prizes. He's a fellow of National Academy of Science India and member of Standing Committee on Women in Science of the Government of India. A main area of interest is computational nanoscience. With great pleasure, I request Professor Shobhana Narasimhan to share her valuable ideas. Welcome, ma'am.
Shobhana is also a fellow of AAS. Yeah.
Pradeep, you wanted to say something?
Nothing. I just wanted to say your recent fellowship.
Oh, okay, thank you. Thank you for that very kind introduction, and thank you for asking me to give this talk. I just want to say a couple of things before I get started. I want to tell you that I've made the talk at a very elementary level. So if it's at too elementary a level, I apologize to those of you who will be bored by it. I also want to say that I've got a rather severe migraine headache today, so hopefully that won't interfere too much with it. How long should I talk for? Do you want to cut it short?
Yeah, well, 35 plus 5 minutes of questions. So we are at, we close at whatever time. We took 12:30.
Okay, so I'll start my timer now. Okay. All right. So I'm going to talk today about the rational design of catalysts. So of course, all of you know what's a catalyst, but I'll just tell you anyway. A catalyst is a substance that increases the rate of a chemical reaction, but is itself left unchanged at the end of the reaction. So I'll start a little bit by telling you about the early days of catalysis. I didn't put in a slide about it, but the first person who did a catalytic reaction, as far as we know, was an Arab scientist in the Middle Ages, sort of in the 11th century or something. We don't know exactly when he lived, but his name was Abu Musa bin Hayyan Jabir. And he made many he's known as the father of chemistry. He was an alchemist, and he seems to have been the first person to have done a catalyzed reaction. This is an example of a term from science that is now migrated to the popular lingo as well. So we use the word catalyst a lot. For example, we say that this pandemic that we're currently experiencing can be a catalyst for change in many ways. So let me start by asking you what you feel was the most important discovery of the 20th century. And of course, many people will have different answers. You might think it's the discovery of penicillin or the car or the airplane or the TV or the internet or computers. But several people believe that the most important discovery of the last century was actually the Haber-Bosch process. So this is an article from Nature, which says that without ammonia, there would be no inorganic fertilizers. Nearly half the world would go hungry. And of all the century's technological marvels, the Haber-Bosch process has made the most difference to our survival. So I'm sure most of you have heard of the Haber-Bosch process, but I'll remind you anyway. It is a process to take nitrogen from the air, combine it with hydrogen, and convert it to ammonia. And it's usually carried out over an iron catalyst. So this is sort of a cartoon representation of it. The green atoms are nitrogen atoms. So you have a nitrogen molecule. I'll just wait a sec till it starts again. Here, nitrogen molecule comes down, hydrogen molecules come down. They are absorbed in the iron catalyst, bonds are broken, and then they recombine to form ammonia. So Why is this important? Well, plants, as you know, need specific forms of inorganic nitrogen to grow. And people realized this a long time ago, but the question was, how do you supply this? And in the early days, people used organic sources of nitrogen. For example, they used to use ground up bones. They would use animal bones, but they also used to use human bones. So for example, people used to scavenge in battlefields where there were large numbers of corpses and use those bones as fertilizer, which is a rather gruesome thing. And after the development of the Haber-Bosch process, ammonia-based compounds started being widely used as fertilizers. They're also used as explosives. So this was in the news a couple of months ago when a large amount of ammonium nitrate, which was stored in a warehouse in Beirut near the port, exploded. And as you probably remember reading, it caused massive damage to the city of Beirut. Large parts of the city were destroyed, and that's shown in this picture, the explosion of ammonium nitrate. So why is it considered so important, this Haber-Bosch process? So this is showing the world population versus year in the last century and up to the present day. So the blue curve here shows the world population, and the red curve shows, the curve at the bottom first, the gray curve shows how much of the world is fed by synthetic fertilizers. So the red curve is estimating how much our population would be able to be sustained if we did not have synthetic fertilizers. So if we did not have the Haber-Bosch process to provide us with these ammonia fertilizers. So you see that there's this big difference between the red curve and the blue curve. So if you didn't have this Haber-Bosch process, we certainly wouldn't have such a huge population. Now you could argue that it's good or it's bad that we have such a huge population, but you can't argue that it's certainly made a big difference to our lives that we have such a large population. So because it was such an important discovery, in fact, in Germany, in those days, they used to advertise it saying it was Brot aus Luft, which means bread from the air, because the nitrogen was taken from the air. So after the First World War, the first Nobel Prize that was given in 1918 was given to Fritz Haber, who developed this process. It was a rather controversial Nobel Prize because he not only developed this process, but he also worked on poison gases for the German army. And so a lot of people considered him a war criminal, and they thought he shouldn't be given this Nobel Prize. And a few years later, Karl Bosch was also given the Nobel Prize, and he was given it in recognition of his contributions to the development of high pressure methods. So he worked on how this process could be converted for industrial use, because you need very high pressures and high temperatures for this process to work. How did they decide that they should use an iron catalyst? So actually, Haber himself did not use the iron catalyst, and he used, I believe, an osmium catalyst or a ruthenium catalyst. And in the factory, they tested about 2,500 different materials. It was done by a group headed by someone called Middaj. And they found that osmium was better, in fact, than iron, but osmium was a very rare and expensive metal. In fact, it was estimated that at that time, in the whole world, only about 80 kilos of osmium were available. And so iron was not as good a catalyst, but it's obviously much more abundant and much cheaper. And that is why they decided to go with iron as the catalyst. So our lives certainly nowadays depend on catalysis in many ways. There's a huge worldwide use, and 90% of chemical manufacturing processes involve catalysts, and it's estimated that about 1 to 2% of the world's energy consumption is used just for the Haber-Bosch process, which is a huge amount. Also in our bodies, catalytic processes are going on. Enzymes are proteins that act as biological catalysts. For example, in this animation here, it's showing one of the enzymatic processes that goes on in our bodies. So if we consume sucrose, which is table sugar, then an enzyme, a catalyst called sucrase, helps break it up before it can be absorbed in our bodies. It's split into two simpler sugars, fructose and glucose, which is the process being shown here. So what does the catalyst do? This also you probably know, so please excuse me if I'm repeating stuff that you already know. So in a chemical reaction, as you all know, interatomic bonds that tie atoms and molecules together are broken and new bonds are made. So this is an example of a chemical reaction is being shown in this picture, where you have a chlorine molecule on the right and a benzene on the left, and they're coming and reacting to form hydrogen chloride and a benzene functionalized instead with the chlorine. Okay, so to break a bond, as is happening in that process, you need to supply energy. So you stretch the bond until it breaks. And to do that, you have to supply some amount of energy, which is shown schematically in this graph. So you have to climb this energy mountain. So this energy that you supply is the activation energy. And the higher the activation energy, the more difficult the reaction is, the more rare it is, the slower it is. There is a slight subtlety here, because though I'm calling it a mountain, in the energy landscape, the topography is not actually a mountain. It's not a peak, it's a saddle point. So I'm showing you that schematically here. I've taken a photograph of Cape Town in South Africa. So supposing you have a pirate by the seashore, I put a picture here of Captain Jack Sparrow from Pirates of the Caribbean, and he wants to reach some treasure, which is over here. So this is like the initial state, and this is the final state. So you want to go from here to here, but to do that, you have to climb over this mountain. Now, how do you do that? You could do that by climbing over the mountain peak, but that's not a very smart thing to do. It takes a lot of time, it takes a lot of effort. So the much smarter way to climb over the mountain would be to take this path. And if you look at the point that you cross over here, it's not a peak, it's instead a saddle point. So it is curved this way in one direction, and it is curved this way in the other direction. So that's exactly what happens in a chemical reaction as well. You climb over the saddle point in the energy landscape, and the height of that barrier is the height of the saddle point. So what does the catalyst do? We want to flatten the curve. This is an expression you hear a lot these days. We want to flatten the curve, so we want to reduce the height of the barrier. We want to reduce the height of the saddle point. So instead of climbing this high saddle point, we would like to climb a flatter one instead. So instead of struggling to climb up, you can gently stroll up this flatter peak. How do you climb? How do you flatten the curve? This is just a little joke animation, which is saying how you flatten a curve. You just wait a bit, and then instead of standing up, you just lie down and the curve gets flattened. But here it's showing what actually happens, how catalysts flatten the curve. So this is again the Haber-Bosch process, again an animation of it. But now this is a more realistic depiction of what happens. So let me show you. This gray surface is the iron catalyst. And now let's see what happens. A nitrogen molecule comes and sits on the surface. And then hydrogen comes, you see the nitrogen bonds are broken and you have nitrogen atoms. The hydrogen bonds break, you have hydrogen atoms. And then they come together and you form one nitrogen hydrogen bond, then a second nitrogen hydrogen bond, and the third nitrogen hydrogen bond. And you now have ammonia adsorbed on the catalyst and it is dissolved and you have ammonia molecules. So this is what the catalyst does. It allows this bond making, breaking and making to happen. So why is that easier to happen on the catalyst surface than in the gas phase? So what I showed you is what's called heterogeneous catalysis, where the reactants, the nitrogen and the hydrogen are in the gas phase and the catalyst is a solid, which is the iron. So why are they weakened on the catalyst surface? This is sort of a hand-waving argument, but when atoms have more neighbors, they tend to sit farther apart, and then it is easier to break the bonds. So I've shown you sort of a cartoon analogy here. So if you are in a crowd nowadays, in coronavirus times, you have to sit far apart and it is easier to perhaps break bonds between you. But if you're just a couple, then you don't have to be socially distanced and you can maybe just sit close together in your house. Or another analogy I can tell you is if you just have one best friend, then maybe your bonds are really, really tight and it is very hard to destroy your friendship. But if you have a lot of friends, then maybe your friendships are not so close and it would be much easier to disrupt those friendships. So it is the same way for atoms. When they sit on the catalyst, because they have more neighbors now, it is much easier to break those bonds. So the steps in the synthesis of ammonia were really understood almost 70, 80 years after the process was first discovered. And this is a picture of Gerhard Ertl, who was an experimentalist who contributed greatly to our understanding of the processes that were involved. So here again, I have shown you sort of snapshots of the different process steps in the synthesis of ammonia and the Haber-Bosch process. You see here, the white is the nitrogen, the blue is the hydrogen. And one of the important things that Ertl showed us was that the rate limiting step in this process is this one here, which I have circled here, which is where the nitrogen bonds in the nitrogen molecule are broken to form two nitrogen atoms. So what is the rate limiting step? The rate limiting step, a reaction usually has many steps, and the rate limiting step is the slowest step, so the step which has the highest activation barrier, and that determines the overall rate of the reaction. So here again, I've shown you an analogy. This is something you will see often. If you have, say, traffic going in many lanes, okay, so this is not very realistic perhaps for India because the traffic is mostly moving within its lane, whereas for us it's much more chaotic generally. But supposing suddenly you narrow from 4 lanes to 3 lanes, maybe there's an accident, maybe there's a bridge, maybe there's some lane is closed for some reason, then the traffic slows down there because you've narrowed it down. And that slows down the traffic everywhere. So it's a bottleneck. So it's the same way with the reaction. If you have one slow step, the whole reaction is slowed down. The other thing I wanted to tell you is that it's not true that every attempted jump over the barrier is successful. So here is an animation. It shows now instead of friendships, I'm showing you an analogy with a high jumper. He's trying to jump over and he is failing repeatedly. But as you know, if you've been watching the Olympics or something, you might fail a couple of times, but eventually you succeed. So that is what's shown in this animation. This is showing another process. This is carbon monoxide oxidation. So let's watch it again. you see carbon monoxide coming down. There's oxygen on the surface. It's trying, finally it succeeds in picking up another oxygen and going off. So you see that you have to attempt it a few times before you succeed. This is a reaction that happens. This is also an important reaction. For example, it happens in car exhaust. Car exhaust has carbon monoxide, and carbon monoxide is obviously very toxic and poisonous. So you have to oxidize it to carbon dioxide before you can emit it into the atmosphere. Of course, carbon dioxide is also bad because it's a greenhouse gas, but at least it doesn't kill you immediately. So now I come to the main part of my talk, which is about designing better catalysts using what is called rational design. So what do I mean by a better catalyst? It might mean that it's a faster catalyst. It could be a cheaper catalyst. It could be a more selective catalyst, because you may have lots of different competing pathways in the reaction and you want to favor one of them. It might be more stable. It might be resistant to degradation. It might help the reaction take place at a lower temperature or lower pressure. By cheaper, it could mean that you need less costly materials, or you might need smaller quantities of very expensive materials. So that's why I put this joke here about the nanotechnology lab, because nowadays a big trend is to use nano catalysts, where you use really, really tiny catalysts. So how do we design a better catalyst? How have we obtained the catalysts that we have been using today? So I told you that Mitash tested about 2,500 materials before he decided to use iron as the catalyst for the Haber-Bosch process. By now, it's been estimated that about 250,000 catalysts have been tested for the Haber-Bosch process. But this sort of trial and error, or sort of brute force method, is it really the best approach that we can use? So what we want now is to replace this kind of approach by what's called rational design of catalysts. And this requires a to and fro between theory and experiment. So theory plays an important role in this approach. Atomistic simulations of the kind that I do. So to really understand how catalysts work, we need to understand how atoms and molecules move and how they make and break bonds. And to do this, you need to perform quantum mechanical calculations. And today, calculations are faster and cheaper than experiments. And they can also sometimes give us information that experiments cannot. What technique do you use? You usually use what are called first principles or ab initio calculations. One uses something called quantum mechanical density functional theory, and that's the approach that I use. It's called first principles calculations because the only input in principle is atomic numbers and atomic masses, and the output is fairly accurate values for the energies and the properties of the system. And for developing this method, the Nobel Prize was given to Walter Kohn in 1998. I will just spend a couple of minutes trying to give you a rough idea what density functional theory is. So the basic Hamiltonian that you want to solve for any such problem is it's a many-body Hamiltonian. So you have the kinetic energy of the nuclei, the kinetic energy of the electrons, the potential energy between nuclei and electrons, and the electron-electron interactions. So you can make the Born-Oppenheimer approximation. So you separate out the electronic Hamiltonian from the nuclear Hamiltonian. And so the electronic Hamiltonian has a kinetic energy and then the potential energy between the nuclei and the electrons, and the potential energy between the electrons. And it's this electron-electron Hamiltonian that's a problematic term because it makes it a many-body problem, which we don't know how to solve. And density functional theory is a way of including these troublesome electron-electron interactions. And instead of telling you the equations, I will again resort to an analogy. So what you do, what Walter Cohn showed how to do, is to map the many electron problem onto an equivalent one electron problem.
Yes.
So it's like, supposing you have two genders of people, okay? So let's assume that, say, the blue men are like the nuclei and the red women are like electrons, and they have complicated interactions amongst them. And the problem you're trying to solve is to arrange them in such a way that you achieve a global level of happiness, okay? The most happy situation for the whole arrangement of people. That's like finding the lowest energy solution. This is obviously a very complicated problem to solve. What you replace it by is you replace it with this problem where you just have one woman, one electron, whom you have to move to find the most happy situation. This is obviously a much easier problem. Obviously, you have to pay some price, and the price is you have an extra term in the Hamiltonian, which I have schematically indicated by putting these masks on these people. And these masks represent something called the exchange correlation interaction, which we don't know exactly. We know it exists. We know an exact form for it exists, but we don't know what it is. But anyway, this is this mapping. And because this mapping exists, and we have pretty good approximations for this mapping, that is what makes this whole approach feasible. So what we do is we do these calculations on, say, different catalysts, and then we analyze our results, and then we get insight into design principles. And once we have this insight, we can use it to design an even better catalyst. So scientists have now learned many design principles for catalysts, and I will discuss maybe two of them I'll have time for. One is called the Sabatier principle, and the other is tuning the position of the D-band center. So the Sabatier principle is actually a rather old principle in catalysis, but people are still using it very successfully nowadays. So it's this idea that in heterogeneous catalysis, the best catalysts bind the atoms or molecules with intermediate strength. So how I word it is the catalyst should be sticky, but not too sticky. And it was first articulated by Sabatier, who got the Nobel Prize in 1912 for his method of hydrogenating organic compounds in the presence of finely disintegrated metals. Those finely disintegrated metals were the catalysts in that case. So the catalyst should be sticky. What do I mean by that? The molecules that are reacting should get adsorbed. That is, they should come and sit on the surface of the catalyst. And this stickiness is measured by computing what is defined as the adsorption energy of the reactants or products on the catalyst. So how strongly they bind on the catalyst. And this adsorption energy depends on the molecule, it depends on the catalyst, and how the atoms are arranged on the catalyst, that is on the Miller indices of the catalyst surface. So here I'm showing again this cartoon of the ammonia reaction. And these molecules had better come and sit on the catalyst. What happens if it's not sticky enough? Then you would have some situation like this where the atoms or molecules just come and they bounce off the surface of the catalyst. So that's no good for us. But if the catalyst is too sticky, that is, the adsorption energy is too high, the products at the end of the reaction will stay stuck to the catalyst instead of flying away. Okay, so here, this is what we want. We want that after the reaction happens, the ammonia should detach. So if the catalyst is too sticky, that won't happen. So how can you tune the stickiness? One way to do it is you can change the elements that the catalyst is made out of, and you can use the Sabatier principle to optimize this. So that is shown in this graph. So look at the synthesis of ammonia again on different transition metal catalysts. So on this y-axis is the rate of the reaction, how good a catalyst it is, and on the x-axis is the adsorption energy of nitrogen, which is a measure of the stickiness of the catalyst. Okay, so notice that Okay, so this is what is called a volcano plot. So notice that the intermediate stickiness, so these are too sticky, these are not sticky enough. The one that's the best catalyst is ruthenium, okay, which has neither too sticky nor not sticky at all. Now you may say, wait a minute, you told me iron is the best catalyst. Where did this ruthenium suddenly pop out of? Actually, ruthenium is a very good catalyst for this reaction, but it's not used much commercially. Some people do use it because it is just much, much more expensive than iron. Like iron costs about 3 paisa per gram and ruthenium costs about 850 rupees per gram. I also told you about osmium. Osmium is not shown on this graph. It would come somewhere here, a little bit to the right of ruthenium, a little bit below. Now, you can design, for example, you can do calculations and look at other combinations. For example, you can look at alloys. So if you look at molybdenum and cobalt, and you take a cobalt molybdenum alloy, the stickiness you have is somewhere intermediate. So you would have cobalt molybdenum falling somewhere here. So that suggests that it would be a better catalyst than iron, while still not being as expensive as ruthenium. So this is one way of designing a better catalyst. The other design principle I'm going to tell you about is what's called the D-band center. So if you look at the interaction between the adsorbate and the metal, when the adsorbate comes, it has, say, some energy level, and it couples to the transition metal catalyst. It couples to the S electrons of the catalyst and it broadens, and then it couples to the D electrons and it splits into bonding and anti-bonding states. And you have stronger bonding if the anti-bonding states shift upwards and become empty, and the bonding states shift downwards and become filled. Okay, now I want to finish up soon, so I won't go into much detail about it. But these two gentlemen, Jens Norskov and Björk Hammer, they define something called the D-band center. That is, you look at the density of states of the D band of the transition metal. So you don't have to calculate the activation barrier. You don't have to calculate the reaction pathway, anything. You just look at the transition metal catalyst. You look at its density of states, calculate the center of gravity of where the D band is. And the idea was, what they said was, the closer the D band center is to the Fermi level, the better the catalyst. Okay, so now what about gold? Okay, I want to talk a bit about gold. Gold, we value it a lot, partly because for jewelry and all, because it's not reactive. It does not get oxidized, for example, unlike silver. But there is this surprise, which is that nano-sized gold becomes friendly in the sense that it becomes reactive. And it was discovered in 1987 that gold nanoparticles can be good catalysts. So you can use this D-band center arguments to explain why that happens. So if you calculate the D-band center for an extended gold surface and then a stepped gold surface and then a gold nanoparticle, you find that the D-band center moves up and up and up towards the Fermi level, and it also becomes accordingly a better catalyst. You can also use this D-band center to design new materials that are better catalysts. And the ultimate nanocatalysts are single atoms, which is a hot field now. So I'll just spend my last few minutes telling you a little bit about what we work on in my group. We've been working partly on how to change the shape of gold nanocatalysts, nanoparticles, to make them better catalysts. This was work done by my student Nisha Mamin. We predicted that if you dope the oxide substrates that nanoparticles are deposited on with an electron donor, you would change the shape. And this prediction was subsequently confirmed experimentally by the group of Freund in Berlin. So this is, on the left, there's an STM image of nanoparticles on undoped oxide. On the right, it's an STM image on a doped oxide. You see the shape has changed from a clumped up nanoparticle to a flat nanoparticle. Then we have calculated the reaction barrier for oxygen dissociation on these flat nanoparticles, and we have shown that indeed the activation barrier for this oxygen dissociation is reduced. So we have made it a better catalyst. The other thing we've been looking at is, I told you about stability of nanoparticles. Now, if you have nanoparticles, this is again gold nanoparticles. Look at these two nanoparticles here. You see that they are moving, and eventually they will fuse together and they will do what is called sintering. That is, the nanoparticles will coalesce together. It is always energetically stable for nanoparticles to fuse and sinter. And this means that the catalyst gets degraded because you get bigger and bigger nanoparticles. So we've been studying this process, and to do this, we've been studying how nanoparticles move and the processes by which they move and the energetics of how they move. And so we've been studying that a single atom, this is, for example, platinum atoms, a single platinum atom moves by process of hopping. Two platinum atoms have a different process. They move by what is called cartwheeling. Three particles, a three atom cluster moves by what we call AT-AT walking from the Star Wars movies analogy. Four atom particles move by rolling, and we've also calculated the energetics by which the particles move, and then they coalesce and sinter. So the last minute, I'll just tell you some current challenges in catalysis. The race is on to find better catalysts for many reactions, and some of the most important ones are catalysts for water splitting, that is to split water to generate hydrogen from water. Catalyst for carbon dioxide conversion. So there's carbon dioxide is a greenhouse gas, so you want to remove it from the atmosphere and convert it to more useful products, for example, methanol, which you can use as a fuel. And also the Haber-Bosch process, as I told you, it's a very high pressure, high temperature process, consumes a lot of energy, causes a lot of pollution. So if you can find a better catalyst for that process, ammonia synthesis, that's also a big challenge. The last slide I have is just a sort of joke slide to tell you that some people, there's a company called Catalytic Clothing, and they have making clothes which are embedded with titanium nanoparticles. And they say that these titanium nanoparticles can absorb our catalysts that will absorb pollutants from the air and thereby purify the air. So thank you. That's all I wanted to say. And I've gone 1 minute over time. Thank you.
Thank you very much, ma'am. It's a privilege to listen to you. You started from Haber process, a start of industrial revolution, to rational design of catalyst. And all the participants enjoyed well. I request the participants to share your questions.
So can I ask or do I have to write?
No, go ahead and ask. You're unmuted already. Go ahead.
Yeah, okay, thanks. Shobhana, so these platinum things, which of the mechanisms is more plausible? The single atom or two atoms or three or four?
You mean energetically the barrier?
Well, what happens in reality, would you say?
So it depends very much on the element. So that's what we found, that, for example, for platinum atoms, it is very energetically unfavorable for the monomer to diffuse. And when we studied the process of sintering, we found that what happens is it sinters by a process of what is called monomer addition. That is, one atom at a time is added to the cluster. But counterintuitively, you would think when that happens, it would be the single atom diffusing and attaching to a bigger cluster. But in the case of platinum, it is, unless you have a really gigantic cluster, for small clusters, it is more energetically favorable for the larger cluster to diffuse and then attach itself to the monomer, because it's very energetically unfavorable for the single atom to diffuse. But for gold, this is not true. And for gold, the particles sinter by what is called particle migration and coalescence. So for example, if you have the clusters migrating and then coalescing rather than one atom at a time being added.
Yeah, thanks. That's what I was just wondering about the platinum part.
So Shobhana, what is this basic aspect of, very fundamental aspect of stickiness? What is stickiness?
So stickiness is, well, it's the absorption energy. So it is how, it is the ability of a catalyst to absorb atoms onto it, which transition metals do with sort of intermediate strength. It's a function of their having empty orbitals and the energies, where those energies are positioned of those empty orbitals. It's a question of how much you bind things to, and the idea is of the Sabatier principle is that you should not do it with neither too weakly nor too strongly. And I mean, technically, I define the stickiness as the adsorption energy of the products or the reactants. Is that what you're asking me?
I was, yeah, very nice. But I was interested in the subtle change in the ion group. What is that deciding that stickiness?
Yeah, so it is really, it's really a question, I think, of the electronic structure and where the orbitals are positioned in energy, where the electronic levels are.
By a substrate, can you make iron a little bit better by a careful choice of one substrate versus the other?
Yes, I think you can indeed, by changing, for example, the coordination number on the surface by cutting the surface a different way.
Thank you.
How a particular catalyst chosen for a particular reaction criteria. Yeah, so this is again, I mean, it's a hard question, but there are several criteria you have to look at. You have to look at the activation barrier, and you have to look at the selectivity, and of course, you also have to look at the cost. And these design principles that I talked about, you can look at the Sabatier principle, and you can look at the D-band center. These are two possible criteria that you can look at to determine the best catalyst. And of course, there is also the whole question of translating it to industrial applications, because I mean, you may find a better catalyst using your DFT calculation, and then the industry might just decide they're not going to change to it, either because your catalyst is